will give 1 mark will be added for everybody, and I will advertise in the group also. So don't worry. Last time also there was one question which had some ambiguity, so we will handle that. Today we will start with the new topic, which will be basically digital communication and information. So that's the basic theme which will run for the next 2 days. We have expert Dr. Mustafizur Rahman. Most of you know him who are part of QT-01. He took a industry lecture at that time. Later, sir found that some of the topics are very close to his heart. So we requested him. So he suggested that I will take these 4 lectures, and that's where we have him speaking to us on various mathematical aspects, and more so because he did both his post graduation and doctoral program from IIT Kharagpur. Very strong mathematics department, and very strong excellence also is very much considered there. So I'm very happy that being in industry, being on a working day, sparing 2 hours for us and preparing, and he has already sent the slides to us. After the lecture is over, we will immediately upload on Canvas, and he is willing and passionate, as most of you have heard him last time. So without taking much of his time, we have just crossed 250. That's what I was waiting for. Over to Dr. Mustafizur Rahman. He works with IBM Quantum Division in the IBM Research Lab. He's based in Bangalore, and he's an alumni of IIT Kharagpur. We are so privileged that he's there with us. I was there in the last class concluding session. He led us, and today we have him as a teacher, not as an industry expert. I think now we'll see the other face of him as a teacher. So we look at next 4 hours, today 2 hours, and tomorrow 2 hours will be with sir. Dr. Ashish will be there. Dr. Maipal will be there for any queries. So I will take a break. I have some urgent meeting, so I will come back towards the end of the program. So Dr. Mustafizur,
yes,
time is for you. Please take it forward. Some more people will join. Usually around more than 500 are joining on a daily basis. So as the people trickle in, no problem, you can start. So thank you so much.
thank you so much, sir. So thank you so much for this kind introduction, sir, and welcome everyone. So without any further introduction or anything, so let us start. So I think this is a digital communication class, and so first let me know that my screen is visible, right? Some presentation screen. Can you confirm? Yes, thank you. Thank you so much. So so the subject is digital communication and information, classical information theory, and I am pretty much sure that more than 50% audience today, they already have studied this course in their college days, and many of you are already teaching this course. So we do not hope any new information out of this 2-hour session, but I'll try to connect some of the things classical to quantum reason, although today is much on the basic part. Uh, Probably towards the classical part, and tomorrow I'll be no audio. Am I not audible? Hello.
Yes, you are properly audible, sir.
Okay, some of the chat people. So those who are those who cannot hear, please rejoin. Maybe internet issue from your side. Okay, thank you. So today it's mostly on the classical part, classical communication part, and let's start. So there will be 2 topics today. One on the basics of digital communication. Roughly, I'll be taking 1 hour 15 minutes on basics of digital communication, maybe till 3:15 or 3:25, and then another 30-35 minutes on classical information theory. And within the class, I'll be asking you many questions. So please bear with me. Some simple question you just need to chat, like put your answers in the comment box, so that I feel, although we do not in the line of sight face to face, we are in the non-line of sight in a far distance, but make utilization of the technology. Let us interact over the chat box. Okay, so please feel free to stop me any point where you do not understand any of the parts. So although I won't cover the detailed digital communication, that is not possible, just an overview. Okay, so what are the books? So first of all, because this entire course is QT-02, is focused towards the quantum technology, right? Overview. And our focus will be the quantum communication part, which I'll briefly cover tomorrow. So these are the books. So the first is Quantum Information Theory by Mark M. Wild, second edition by Cambridge University, right? And so let me use the marker maybe. Just give me a second. Yes. So the first book is the Quantum Information Theory by Mark J. Wild, and the second is mainly on the classical information by Thomas Covert. And I'll suggest to those who are new to digital communication and interested to understand how the digital communication principle works or want to understand this subject deeply, they should study the reference number 3. Okay, reference 3 is like advanced and one of the best book for digital communication. And I'll suggest to the candidates to please look at these 3 courses available. First 2 courses available on NPTEL. First is on analog communication by Professor Gautam Das, and the second on the modern digital communication techniques by Professor Subrosekhar Das. So these are one of the best available resources on internet for a broad overview of the subject. And the third one is on the quantum optical communication side, who are interested in the optical communication and quantum optics. So this is the reference for you. Okay. So definitely my acknowledgement, all credit goes to GSNL School of Telecommunication, IIT Kharagpur. Although most of my research inclined towards the linear algebra and the mathematical aspects of quantum computation. But I did my master's and PhD from this school, telecommunication, GSNL School of Telecom, IIT Kharagpur. So all credit goes to my teachers. So let's start the communication theory. So let's understand this particular picture. Because I won't cover just simple by going with math and all. Because many of the candidates should get the flavor of the subject more than the just mathematical aspects of it. So by communication, leave the word quantum communication. So I have very less slides today, so only a few slides. I'll mostly use the pen and paper. Just for the motivation part, I'm using this slide. So communication typically, you all know about the TCP/IP protocol or the WSI protocol, right? The different layers from top to bottom layers, starting from application layer to transport layer, right? Several other layers like networks layers, data link layer, and the bottommost that is called the physical layer, right? So that is the how the communication works, right? And you all know the how the internet works. And in the application side, basically there are 3 things within the communication. The first part is communication itself. That means you are communicating data from one point to other point, and I'll take roughly 1 hour what communication means. Then suppose you are sending one message from say place A to place B, and you're sending a message. So your message is basically that is transmitted from place A to B. And suppose you don't want somebody to basically steal your message. Okay, you want to hide your message. That's a secret message from place A to B. And you want to put a security on top of it, or an envelope on top of it, which should not be opened by third party. Who opens it is called a eavesdropper. Okay, so that particular aspects is coming under the security pillar, and all your QKD like quantum key distribution and other things are related with this particular aspect, the security part on the envelope. Okay, I'll come tomorrow on most of the part on it, how the envelope works and all. And the third part is that computing part. So you can ask, what is the computing within communication? So suppose you are transmitting a message X and you are receiving Y, where Y should be theoretically you should receive X, but there are several uncertainties in the environment like noise, the channel interference, path loss, many other things, right? Then how to retrieve given X, how to retrieve X? This is your problem, right? So there are lots of like mathematical techniques to get your message back at the receiver, and that particular part takes care by several mathematical computation or the algorithms. So I'll cover some of them like the least square method or the map method. So these are the part where computing plays an important role. Okay. So let's talk about the various communication system. Why only just cellular communication? So typically, when we say that, okay, somebody is saying something in the chat box. Audio is breaking. Audio is fine. Check your signal. Okay. Okay. So what are the basic building blocks of a communication system? Those who are pretty much new, okay, might not be coming from the electronics and communication. They might be from purely computer science department or physics department or other departments, okay. I assume no background, okay, this is your first class of digital communication and forget about everything else. So maybe this is an overview, and maybe if you are interested more in the subject, you can go the resources I referred. So typically you start with something called a source, okay, and there is something a destination. The basic purpose of communication is that you need to send some information or message. I'll define what information means, and in the next half of this class, just for simplicity, consider it some message, okay. The basic purpose of the communication is to send this information from source to destination, okay, reliably. The word reliably, this is important, and efficiently. So if this message, like reliable means, suppose you send a message with certain information, and at the destination it should not collapse, or it should not, okay, it should not be stolen, or it should not be manipulated, right? It should be intact. The information should be intact. So so that means it should reliably reach. Also, it should be efficient. That means you send some information today and it should not reach after 10 years, okay. So right now, those who are using like 4G, 5G handset, you know, like whenever just you make a call within just a few seconds, or within a second, like few milliseconds, your receiver who is sitting probably at the other corner of the world just get your message or your voice call immediately, right? So that is the efficiency of the present cellular communication system. But just for simplicity, what we do is basically let's denote source by SRC for simplicity, okay. So there is a source, and suppose you are sending a voice message or some message, okay, and there is two part. One is called the source encoder, that encode your message. Source message may be from voice, which is a natural signal like speech signal, and it is converted to electrical signal or some form which is compatible to your mobile handset, or the form where you are transmitting source encoder. And there is a, when it propagates through the channel. So what is channel and all, I'll come to this particular point in more detail. So basically, and suppose here is the destination, okay. So from source to destination, there are mainly three things. One is called the transmitter section, where the message is transmitted. And in the destination, there is something called receiver, which receive the message and reconstruct your message, like reconstruct your signal. And between the receiver and transmitter, there is a medium called a channel. Channel can be wired, channel can be wireless, and there are several kind of channel. I'll come more tomorrow on, like on classical channel, quantum channel, and other thing. But just for simplicity, by communication, we need to understand three things. One is called the transmitter, one is called the receiver, and one is called the channel. So we represent transmitter in short as TX, receiver as RX, and channel, okay. And in the transmitter, there are two important components. One is the source encoder that basically encodes your information, okay, to a form which is basically suitable for the communication through the channel. And in the channel, there may be several impairments, okay. And to mitigate some of the impairments, so there is something called channel encoder. Okay, so that message should not be much impaired in the channel due to the environmental distortion and other things. What are the other things? I'll come later. And after the channel, suppose you are transmitting a message X and you receive Y, and there is some changes H, such that your Y equals to H into X, that H does something on your signal. Okay, maybe it can attenuate your signal or something. In addition, there may be some kind of noise, maybe due to environmental radiations, other things in the hardware, thermal noise and other things. So there is an additional perturbation, additional uncertainty. Okay, so what you receive is basically hx plus w, where x you have transmitted, h is some impairment that is added by channel, and additionally there is some more uncertainty from different kind of sources of uncertainty, maybe thermal noise in your hardware, maybe environmental radiations and other things. So that effectively what it does is y equals to hx plus w you are getting, right? So that's the basic model of communication. In fact, we'll learn more about it. So I told about the cellular communication. Let's understand more. Suppose there is a radar and multiple communication systems, say radar, cellular communication, satellite communication, and satellite communication, and also neuronal communication. Okay, neuronal communication or biocommunication. So let's take for example. So the cellular communication, cellular means your mobile communication, things works like this. So there is a transmitter or an user or a mobile, something like this. Suppose this is your TX, okay, and there is an RX, your friend, you're calling to your friend, and there is a air medium or some medium. Okay, so nowadays it's a air medium. Earlier, before the introduction of GPRS or 1G 2G system, so there was something wired mobile phone, right? Or so there you have seen that these connection were used to communicate from one place to other place. Nowadays it's air. Okay, and there is a lot of evolution. So the note I shared with Professor Pilli, so you will be getting it. So there is a detailed historical development and other details. I'm not covering all these things in 1 hour. Most important principle, which probably will be used in the next session as well in the quantum part. So, so so I'll be covering those aspects because assuming many of you are new. So in the cellular communication, the TX and RX might be sitting at two different places. Say it is Delhi and say it is New York. Okay. So now you can ask me, so suppose I am sitting beside my friend. Can't I call my friend? Yes, you can. You can talk to your friend just sitting beside you. Okay, but if you can talk to your friend and your friend can hear your voice clearly, then what is the need of this mobile phone? It's not needed, right? Voice mobile phone. So typically cellular communication, the basic requirement is that they are placed far apart, and you want to make a call or send a message or send a video from place A to place B. Okay, so your transmitter and receiver are sitting at very different place, where your data model, that is y equals to hx plus w, where x is transmitted, right, and your friend is receiving y, and the objective is when it receives y, now y is not the desired quantity. What is desired, that it has to reconstruct, it's a hardware and the software algorithm should reconstruct x given y. Okay, this is the objective in a cellular communication system. Okay, so just simply retrieving x. Now in a radar, what happens? So radar has most of the radar, but they have varieties and working principle may differ. In general, the TX and RX placed in the same module, same modem. Okay, so suppose there is something called antenna, basically which convert your electrical signal to EM wave, electromagnetic wave, such that it can propagate through air. Okay, so I am taking a transducer and antenna, TX antenna, and there is something called an RX antenna. Earlier you see your TX antenna, transmitting antenna and receiving antenna, they are far apart, right? And there is environment. There might be trees, there might be houses, there might be vehicles, there might be mountain and all. So your signal may be attenuated, and there might be many phenomena like the absorption, right, the reflection, and many other phenomena. Hence, there are two uncertainty quantity. One is H, channel quantity, which can make impairments to your signals, like it can attenuate your signal, it can reflect your signal, many other things, right? It can make delay of your signal, many other things. I'm not going details to that signal model, but similarly, there is another uncertainty. So this is a random variable RV. I hope in some probability class random variable is covered. If not, maybe in the next module, I take a detailed session on the probability theory and I'll cover it. How, what is the role of random variable in classical and quantum communication system or quantum computation system. So H is one random variable and W is another random variable. If they change over time, they can be random process as well. Like H can be a function of time or W can be a function of time. In general, we assume that within certain time, your channel is almost constant or behaving like statically, and that particular time is called the coherence time. Okay, and but in general, channel can vary over time, and the W can also vary. This noise is highly random. Okay, W. So there is some theory called central limit theory, where W is assumed as a Gaussian distribution or the normal distribution with some mean mu and variance sigma squared. For an unbiased process, we normally take mean equals to 0. So all these details I have given in the material. Please have a look. I'm not going to detail, but in general, our objective is to retrieve this X given all these uncertainty parameters like H and W. Okay, so you are getting some Y, your objective is to retrieve X. How to retrieve X, I'll show you, okay, later. So now in a radar system, you are transmitting some X and you are receiving some Y, and suppose your model is some A time X plus some another noise here, W prime, okay? And it sends the signal and it receives the signal, and there is something happening in the environment. What is happening? Maybe some aircraft is going and you are interested to measure the distance from the ground. What is the height of the aircraft from the ground? So ground, your TX and RX is sitting here, you are sending a signal and you are receiving it, right? Or it may be suppose you have a vehicle, right? And this vehicle is particularly a smart vehicle or autonomous vehicle. In front of it, there is some radar TX and RX. The purpose of TX is to send some signal, and the receiver receive the signal. And there is other object, like there may be some pedestrian, there may be the other vehicle and all. And based on the received signal Y, you are interested what is A, what is happening in A. A is environment. Okay, A is coming from your environmental part. That means what is happening means what is the distance from your car to the pedestrian who is crossing the road. When you have two vehicles, okay, just let's go to the next part. So maybe let's take this particular example, how the autonomous vehicle works. Suppose you have two vehicle like this. Okay, so you are sending one signal and receiving one signal X and Y, and you need to estimate what is the velocity of this car, of the in front of car. So this is say vehicle number 1 and this is vehicle number 2. So here to here, here to here. So basically, what is the velocity of the next car that you need to estimate from your Y, not X. Earlier, our objective was to retrieve X. That is the principle of communication. Now you are interested in a model, and that model is basically Y equals to AX plus W. Okay, but we are not interested in X. Okay, we know X, this is known now. This is not, suppose this is known to us. This is some uncertainty parameter, some random variable. Here, A is important. We have to find some information from A. Okay, so we have to estimate some parameter of A, from where we should understand the velocity of the car, acceleration of the car, position of the car, X of X velocity of the car, right? So V of t, A of t, and X of t, or in fact they can be constant quantity. Okay, so there are algorithms like Kalman filter and other things. So depending on the radar principles and all, I'm not going detail. So this is typically called the radar communication system, radar communication. And also nowadays these are called the vehicular communication. vehicular communication. Now, maybe your car 1 can talk to car 2 now. Suppose this is an autonomous car A1 and this is another autonomous car A2, means there is no driver, and suppose this is an ambulance, okay? And you have to design an algorithm such that ambulance has to pass this car, right? Suppose this particular car A1 understand, okay, these are the velocity and other things, and this is not just one car, there might be several other vehicles, okay? So depending on that, those information, it has to change the lane, increase the velocity and all. Then this car probably has to give some information to car A2, car A3, or if there is some pedestrian, it has to put some signals, horn, right? Such that this particular ambulance can go fast, right? So in that particular case, what has to do? In that particular case, why ax plus w, not only a is important, in the second, suppose y1 equals to a1 x1 w1, and the next signal model y2 equals to a2 x2 w2, right? So from the first, you understand what is a hat. A hat means the information about a, or the estimations of some parameter about a, and that information you feed to this model, okay, such that, okay, I can send this information y2. So basically then there is a both communication part, means radar first tx rx, it understands the a hat. After knowing the environment, it sends another signal x2 to the car v2 a2, autonomous car a2 or v2, whatever it is. So then basically this second car has to take some decision to its velocity and other parameter, okay, and it can again communicate to the first car, okay, I am decreasing my velocity and all, and I am taking this decision. So this is called v2x communication, like vehicular to anything communication, or this vehicle itself, they are both communicating. So there is both communication and radar, both particular application. So this together is called the RADCOM technology, or radar communication technology. These are important technology in 5G and 6G. So I'm giving you an overview, not just simple calculations and all, so that you can probably get some flavor of the technology, what is happening. I'll come to this building blocks and all later on. So let's take another example. So I have given two examples, right? One on the cellular, one on the radar. Let's talk about the satellite communication. I'm trying to start some free space, so please bear with me for a couple of seconds. I hope I'll get one. Give me a second. Just for me to create. So I'm very sorry. Actually, I took some time. So now, can you just confirm that the slide is visible or not? Anyone? Yes, thank you so much. Okay, so now now if it is a satellite communication system, so if it is a satellite communication system, so typically in a satellite, So you have some system, right? And there are some and this particular satellite rotates around some orbit, right? So in the ground, so our objective can be twofold. Maybe sometimes we are interested to send some information to the satellite and get some information back. That's the typical communication, like some TX RX communication chain. It may be the case that in the satellite there are cameras or sensors which can collect meteorological data, which can collect the imagery data like the remote sensing data and other things, and can, because it can capture a broad range which cannot be captured in simple terrestrial. So because the field of view of a satellite is much bigger or much larger than the simple normal radar or normal things, so it sends those kind of data directly to the receiver. So it can be a one-way communication, just simple. At that particular point, satellite can be your transmitter and your ground station can be a simply receiver, where at the receiver you get some information of the imagery data or other data to the ground, right? So you simply get some Y, okay? But in this particular case, HX plus W model, X can be some image, okay? Or it can be some thermal data or some other data, and you directly receive some Y, okay? And from there you need to retrieve this kind of X. So it can be many other like satellite communication. There are a lot of applications, but the basic data model is almost same. So why I am doing lots of emphasis on this particular model, I'll come to this particular point again. This is extremely important, this particular linear model, and this particular model again will revisit tomorrow in the quantum communication channel as well. So and the next part is basically the biocommunication or the neuronal communication. So typically you have some neurons in your body, okay, or nerves, and unit of nerves are neuron, and there are typically dendrons, and the branches are called the dendrites, okay. And so this is the cellular body and axon. This is the cell body part. So these are called the dendrons. And this is the body, cell body part. And this is the action part. And there are several brasses. And there again another neuron starts. And all our like thermal and other pressures and other things we receive normally in terms of our neuronal communication. So typically all our natural signal that we perceive, they are some X1, X2, X3, X4, all these signals, they can be thermal signal, electrical signal, or other form of signals, and which passes through this cell body, okay, cell body, and pass through the actions again. So you can again model some Y here that you are receiving, and all the X1, X2, X3 you are getting. So there are weightage of the dendron, say maybe W1, W2, and so on. So effectively what you are getting, sum of Xi, Wi is your signal, okay, and there may be some bias Bi. That means not every person has the same response capability of the neuron. So there might be some physiological limitation of the elasticity limit and many other mechanical and other bio limitations of individuals. So basically you are doing W1 X1 is the weightage of your signal of your X1 input, plus second weight W2 Y2, plus third weight W3 Y3, and so on. And that is effectively you are getting some signal Y, right? And this is the typical biosignaling model. And from the Y, your cell has to decide. There is a typical biological phenomena depending on the action potential and other things, whether this cell should respond or not, yes or no. So if you see the behavior of this kind of signal earlier in the basic communication, what we have done, we probably had you probably have some transmitted some sinusoidal signal in the environment. There is some noise coming, okay, and additionally the signal can be attenuated. If the actual version is something like this, So suppose this is your X and this is the Y you are getting, okay, because of distortion and other things, okay. So this is what the communication things, but in the cellular, you will look like it is something kind of pulse stream or something like this. So the signal, the receiver or the cell has to decide that whether there is a response yes or no, okay. So based on this particular phenomena, technology develops something kind, these are called the, yes, this is linear. So this is kind of, the model that is developed in the AI, artificial intelligence, that is basically mimicking the biological behavior of neuron, and the model is again same. So what it is doing? So it is doing simple like this. So you have a lot of nodes, right? And there are many inputs. Suppose x1, x2, x3, x4, x5, these are the inputs, and there are weightage w1, w2, exact same model, w3, so and so on, and you are getting something, and there is a basically adjustment, that is the bias b1, b2, b3, b4, and so on, and there is a next layer of neuron, okay. So exactly it is doing the same thing. So what it is doing, so this is simply, so people may talk AI differently, but as a communication person, I should say neural network is also an application of your simple biological communication system, where at every layer of your neural network, what you are getting. So now I will simply append all the input as a vector X instead of all the individual input, but the component are X1, X2, X3, X4, X5, right? And I will put all the weight matrix as a diagonal matrix, W1, W2, W3, up to Wn, n number of weight into your all the inputs x1, x2, x3, x4, and xn up to xn. And if you multiply this diagonal matrix times the vector, you are typically getting your output y1 to up to yn minus 1 or yn, whatever it is, right? Depending on the length. So if it is n cross n, it is n cross 1, it is n cross 1, right? And if there is a bias, add the bias, simply b1, b2 to up to bn, right? So what you are getting, some b vector, bias vector, plus some matrix w time x is your input, and what you are getting, some y. So this is the basic communication model, which is same as the neuronal communication model, as well as it is same as in the AI model. So once you get the output of one neural network model, that is the input of your next model, right? And there are some more things. So like this W can be linear, this can be a function of nonlinear function like ReLU and other things in AI. So I'm not covering the AI perspective, but as a digital communication part, let's focus the digital communication. It's not just digital communication. It has a lot of implication, this signal processing part, in many other technology, as well as the quantum technology, which we'll be looking tomorrow. Okay. So this is the introduction of the subject. Okay. How much time I took? Maybe I took a lot of time. Okay. Now, let's talk about signals. Okay. So I forcefully included in our UG syllabus in what we learn about continuous signal, discrete signal, digital signal, and I have introduced the thing quantum signal. Okay. So let's define in a different way what is continuous signal. So let's take y, that the typical example just we have seen. So if you have a domain X, so better let's define in terms of signals. So because it's not the math class, okay, just give me 1 second. So I cannot erase. Fine. So suppose let's take time variable defined by t. So if for every t you get some value y, then we say that y is continuous, where t can take any value greater than 0. So what it means that over time, any point you choose, you will get something here. So it can be something like this. It can be your continuous signal. So where any point t you choose, you should get a value here. So that's why most of the books write in this way, that if your time is continuous, that means so there exist all values of t and all values of y in such a manner that y is a function of time. Okay, so there is a map between time to the signal amplitude or whatever current voltage, whatever you consider. If you get that any value of t you can consider, and you get some value of y, then this particular consideration or particular setup we called a continuous signal, right? Now, in a case where again I'm lacking space, okay. So there is a discrete part. So discrete part is that there is some time t and there is some amplitude values. So definitely you can choose any t, right? But you won't get, so suppose you choose that particular t, so this is maybe t0 and this may be some t100, there are 100 samples, okay, and this is some t13 sample. So at t13 we do not find any amplitude of the signal, right? So at some particular instance of time we get the signal. So that means in this particular case, y equals to ft, this particular definition. Now I cannot just simply say this is a function, continuous function, because for some particular ti, for some ti, not all, for some ti, okay. So for some ti, I will get some amplitude ai. So this is if your a axis, right? So this may be your some a value. This is another a value and so on. So maybe it is your a1, it is your a2, this is a3 up to a some a50 or something like that, or a some value for that particular t. It may be 100. Okay. So here you see that for every ti, not the amplitude is defined, function is defined, right? So for some particular time instant, you can only define your signal. So there is a better way of defining this. Okay, how to do this? So now suppose you consider some domain value t0, t1, t2 up to say tn minus 1. So there are n number of time value, and let's denote by vector t. Okay, so it's a vector and let's denote by column vector. Okay, and I will only get some values of amplitude at those points of time, right? So a bar equals to a0, a1, a2 to an minus 1 transpose. So for some value of t, I'll get some values of the amplitude, right? And I can append all those amplitude given the sequence of time. And this particular way of writing the amplitude in the form of vector is the representation, discrete representation. So normally in most of the books, you have seen that what they are doing, they simply break your t to some nt, where n can be some integers, n equals to 1, 2, 3, 4, 5, and t is the time duration. So suppose you choose n equals to 0, this point, n equals to 1, if this is your t duration, this is n equals to 1, this is n equals to 2, this is n equals to 3, 4, and so on. So if you multiply, this is t, 2t, 3t, 4t, 5t, so on. But this is only valid if you sample this entire time domain in uniform sense. Otherwise, this definition is wrong. Okay. So we won't go by this definition. This is fine for simple thing. But in general, what we'll do, we will do some simple discretization of the time domain. We'll simply find whether the amplitude exists on those samples, yes or no. They may be uniform time samples, they may be non-uniform time samples. And if we get all the values of the amplitude, we will simply write in a vector form and that we'll call as a discrete representation. Okay. Now let's talk about something. Suppose we get h equals to y equals to hx plus w. This is our communication model, and communication may be in various ways. Suppose those who are buying iPhone right now, iPhone 15, 16 Pro or something, I don't know. You will find that in your spec of your mobile, you see there is some spec that is called MIMO antenna. Okay, those who don't know MIMO. Okay, and those who are using some previous versions of mobile, maybe some 4G handset or 3G handset, maybe your mobile does not have this multiple antenna, right? So what this tells about is that suppose you have a transmitter, okay, and there is only a single antenna, so you can send the discrete or some data stream x0 to x1 to x minus 1. So it will go sequentially through this antenna as a EM wave, one by one after doing all the digital communication steps, and you will be receiving through one antenna, RX antenna, so that there will be Y0, Y1, Y2, and so on, and there will be distortion H, say some H. Okay, so this is a simple model. Random variable Y equals to so random variable Y equals to some your hx plus w, say, where h is your random variable coming from your channel. This is coming from noise, and you have transmitted some data stream x, some pilot symbol or whatever it is. Okay, and you are getting some y. Okay, but nowadays people are talking about multiple antennas. And how much these antennas will be, there are lots of technology: massive MIMO, large MIMO, ultra massive MIMO. There are a lot of things. Okay, so more antennas are there, more diversity and other efficiency and data rate you can create. So now suppose you have this kind of setup. So more antennas are there at the TX and RX. So here you can instead of just simple one by one sending the data, you can send one entire data stream through one antenna, another entire data stream. So I'm putting bar means a big vector, some vector. Okay, and x3 is another set of symbols through the third antenna, and so on. Suppose there are 256 antennas. Okay, or the 512 antennas, lots of antennas in 6D or 7D. So you can transmit lots of data at the same time, and in the receiver you are getting lots of data, y1, y2, y3. So these are not single data point, these are in fact vectors. Okay, so what I am saying is that suppose you are sending say 1000 data points as a vector, as an input to one antenna, another 1000 through second antenna, another 1000 to third antenna, and so on up to 256 antenna. So together you are sending 256 into 1000 data points. Okay, and at the receiver also you are receiving that much data. Now this antenna can directly communicate to this antenna, but it can also create interference to the second antenna, third antenna, fourth antenna, and so on. Similarly, here to here, here to here. So there might be many channel coefficient. That means what is happening? So suppose if there are two antennas, so 2TX, 1, 2, 1, 2. So then basically it can directly communicate with this with channel coefficient H1, 1, I'm saying. So this is transmitter, this is receiver. This can directly communicate with this. This is H22. It can communicate to this one, so H21. It can communicate this to one, so you can call it as H12, whatever it is. Okay. So now you can define this entire channel matrix H as H11, H12, H21, H22, right? And now you are receiving Y1, Y2. You embed them as a single vector or matrix, whatever it is, because if x1 is itself is a vector, x2 itself is a vector, so y1 is one vector, y2 is another vector. So you define a capital Y bar, capital X bar. So your capital Y bar is defined as H capital X bar plus some W capital. Okay. So this is your MIMO signal model. Okay, so the question is there so the question then is there these individual antennas behave like multi-element log periodic one? Okay, so there are many configuration how you can orient the antennas, like linear array, spherical array, or the like. So there are configuration. I'm not going detail to that. Yes, you are correct. So you can do probably, but again we have to check many other performance metrics and all. So while I am talking about the variable, that is the continuous, discrete signal and all. So why I am talking these things? Let me define why this is important. So when from the nature we receive some signal EM wave, any natural signal is basically continuous. Natural signals are continuous. It can be temperature, anything. When we perceive it, they become discrete because of the capability of the observer. Okay, nature is continuous, but when we try to communicate them, we forcefully discretize it because of the limitation of your hardware or the observer. Okay, so you are receiving some y which is continuous, actually naturally, which is continuous. You are forcefully discretizing it, means you are getting some y0, y1 to some yn minus 1, right? And depending on the stream of data point y, you have to take the decision. In radar, if it is a radar problem, then you have to decide whether there is a target or not, there is a flight, aircraft is moving or not, right? So if your decision is yes or no, first of all you have to say whether I am receiving the signal or not. You can directly simply receive noise, not signal, simply noise. Suppose your model is hx plus w, but maybe the case that you are only receiving w, not the signal. That can be the case, right? So first you have to speak that what I am receiving, whether the signal at all present or not. And this particular problem is called the detection problem. There are a lot of theory like Niemann-Pearson algorithm, the Bayesian algorithm and all. Now suppose you say yes, I am receiving the information, yes. Okay, so I'm talking with respect to radar. So first radar, we have to confirm that there is a target. Then we have to say, once we say okay there is a target, then what are the parameters, what is the height, velocity and other things. If we say yes, then what is the estimate of the parameter from the signal y. Okay, so this is particular problem is called the estimation theory problem or the estimation problem. So there are two parts in statistics. So that is called the detection problem and the estimation problem. In communication, estimation is performed first. First we estimate something, then after getting the estimation, we take the decision, okay, this is 0 or 1. The what was transmitted, 0 was transmitted or 1 was transmitted. This is the vice versa thing. So there are some mathematical twist in it. So now let's talk about the this particular phenomena, which I already shared the notes with you. I won't go detail of that. So what is happened? So when you were sending some message from source to the so this is entirely a transmitter chain, TX chain. So earlier I have said that there is a transmitter, there is a channel, and there is a receiver. So this entire thing is related to the transmitter part, and I highly recommend to cover the digital communication lecture series of NPTEL I referred initially to know individual details. So what is happened is that you send some signal xt, but your hardware won't process this much information because t is greater than 0, means t can contain infinite values. But can I store infinite values in the hardware for time information or the amplitude information? No, right? Yes, I'll come to quantum signal, sure. So I cannot store all this information in the hardware. So there is a suitable process of discretization and all. And one of the processes is called the analog to digital conversion, ADC. Okay. And in the ADC, there are several blocks like analog source, sampling of the time, then sampling of the digitizing of the amplitude, that is called the quantization. Then whatever quantized value you get, you do some algorithm, that is a source encoding, and you encode the information to some bit string. So suppose you have some xt, and from that you get some digital bit string 01, 01, 11, something like that. So this entire process is taken under the ADC. But there are additional procedure due to channel and other kind of distortion, how to mitigate that. So there are several blocks like scrambler, CRC, FEC, interleaver and all. And then basically once you cover all the steps and you again form a kind of analog kind of nature of signal from digital to again analog. Now you can ask me, earlier already it was analog, why shall I do digital again analog? Because again you have to transmit as an EM wave to the nature, right? So you do some DAC conversion, some suitable form of natural signal, okay, nearly natural signal. And in the RF zone, because it's a low frequency signal, so you have to do a frequency conversion, other things in the RF section, radio frequency section, and finally you can transmit to the receiver. Similarly, there is a receiver block. So there is a detail of the receiver. I'm not going to cover these things. So given some Y, how can I retrieve some X? So this is the entire block of this. So better I'll cover the quantum signal parts, because in 1 hour covering everything is difficult, but the important part. Now, so we have some continuous signal, right? T versus some say for example xt, right? But if I draw any continuous signal in this way, this is in fact a wrong drawing, okay? Because if I cut these things, that means already it is like this is not, so t should greater than 0 should go on, but this is just a snapshot of the continuous signal. Similarly, we can do a discretization like this, and instead of xt right now I will write it x bar, okay? So because this x bar constraint contains the point x0, x1 to up to xn minus 1. Now comes the quantum signals. Okay, the direct answer is you do some x to get x. Now how to do x to get x? That is the question. So I should tell this much more in some quantum computing session if I would take, but for simplicity, how should you do? You convert this. So here you have some two kind of information. One is the domain information or the time domain information. One is the range information or the valued information, the range information or the amplitude information. So in time, so it's a domain is t definitely, and range is some voltage level or the current level, something like that, right? In discrete, you do something T0 or some T1 to so on, and this may be discrete voltage level x1, x2, and so on, right? In digital, what you have done, you suppose converted this y-axis after ADC. What you have done? So what you have done is that suppose between 0 volt to 5 volt, you have done some L level quantization such that it is 0 0 0 to 1 1 0. So 0 0 1 up to 1 1 1, and whichever is the nearest point, you call it that particular. Suppose this is near to your 0 0 1. So this particular x0 to digital encoding is 0 0 1. Similarly, x1 has some 1 1 1. So as a whole of entire information, what you get some 0 0 0 0 1 1, some 1 1 0 or something like that. So this is your data stream, digital stream, right? Digital signal or digital stream. Some I'll call it some x, say for example. Okay. Now the quantum signal. So what you have to do? You have to do. So earlier, your information is encoded in the binary string. This is important. Binary string, right? But quantum, we won't do these things. What we'll do? The domain, this T part, we will do the domain part. We will discretize first. And let's say we do this domain part. So this is not written in any book based on my PhD and work experience. I am just explaining. You may find a different way of representing the quantum signal in some research paper, but this is what I understand or our group understand. So what we do is typically you suppose we take 5 qubits, okay? Or it may be some 3 qubits for simplicity. So what are the possible states of 3 qubits? The states are again 0 0 to all 1 1 1, 0 0 1 to all 1 1 1. So we call this x-axis or the horizontal axis or the time axis or the domain axis, we call it as a domain as all your computational basis 0 0 0 0 0 1 0 1 0 to up to 1 1 1. Some point it is 1 1 1, right? Now we are not storing the information in this 0 0 1 1 in this axis. We will be storing them in the probability amplitudes. So this particular encoding is called the amplitude encoding. There are other encoding schemes. Maybe sometime I'll say when I'm saying I cannot encode information here, I can encode, but not this way. that is called the basis encoding scheme. So this particular domain is called the basis. Earlier this was our time axis, this was our domain. Now it is called basis, okay, in quantum, because every information right now here should be represented in terms of vectors, not scalars. Okay, so when I talk about vectors, they should have some basis, right? How the vector is represented. So these are the basis states. Okay, so now what I'll do, I will assign some probability of these states. Maybe this is the probability of these states. This is the probability of these states. This is the probability of this state. This is the probability of this state. This is the probability of these states, so on. Now, what quantum postulate says? Quantum postulate says that if these are the probable states, probable bases, okay, and I call the probable basis at some bi, and they have some associated probability amplitudes p1, p2, p3, and so on, pn. Here it is p11, so it is p8, say, for example. Okay, so if the associated probability is pi, then this entire pi bi should represent my wave function for all I. This is the definition of wave function, right? Such that the sum of probability equals to 1, right? So I defined x2 ktex, right? Then this ktex should have a representation pi bi, where I may be equals to 0, 0, 0, 2, 1, 1, 1, or it can be from 0 to 2 to the power some little n is the qubit size. Okay, fine. Some 0 tensor product n to your 2 to the power n states, 0 2 to the power 0 tensor product 2 to the power n. Okay, so pi bi, where bi is your basis states, and now your information is stored as the probability amplitudes of those bases. Okay, this is important. So what I have done earlier, so this is looks very close to discrete signal, in fact, not digital. This is, we have to look at this. Now, these amplitudes earlier, this voltage level, current level, earlier can take any value. Now they are the probability value. So probability value means pi between 0 and 1. Probability should be between 0 and 1. And quantum postulate says that if there are n number of states, then the sum of all probabilities should be equals to 1. So this is the complication of quantum signal. I hope it is clear. Anybody? You can ask me question. I can stop here for 2 minutes. So this is the definition of quantum signal. You can encode images, you can encode speech signal, you can encode anything, because you are attending the FDP. And I assume if there are 1,000 people who are attending FDP, at least 10 people out of this 1,000 should write a paper on quantum signal. So when I started PhD on quantum signal processing, there was hardly any paper. So fortunately, I got my PhD. I didn't hope that I'll complete my PhD, but right now I look, there is a lot of opportunity and potential in this subject. So any question, please? We can encode optical signal. Yes, you can encode any signal, but yeah, so here each discrete signal represents probability or probability amplitudes. Nice question. So, okay, this I have to go back to the quantum computing thing. Okay, nice, no problem. I love this question. Okay. Again, let's go back to the slide. Suppose in some classes you have seen the quantum state representation on Bloch sphere, right? Bloch sphere look like this, where this is gate 0 and this is gate 1. Sorry, this is gate 1. And there is a plane that is called the Hadamard plane and all, and there is some information gate y. But let us represent the signal from Bloch sphere to Cartesian coordinate system. What we have learned from our class 6. Okay, Cartesian coordinate system. There is an x-axis, there is an y-axis. Okay, y-axis, x-axis, right? And instead of x-axis and y-axis, let's call this axis, because x and y are orthonormal, right? Orthogonal or orthonormal. Now, So orthogonal means the 90-degree part, means dot product between x and y is basically 0. In addition, if norm of x and norm of y, they are 1, then basically we call it as orthonormal. Okay, if this condition number 1 is satisfied, we call orthogonal. If both condition 1 and 2 satisfied, we call it as a orthonormal thing. Okay, so now let's look, without taking x and y, let's take ket 0 here and ket 1 here. Now ket 0 and ket 1 are orthogonal vectors, because definition of ket 0 is basically your 1 0, and definition of ket 1 is basically your 0 1. And if you simply multiply these two vector dot product, inner product, if you do, you will be getting 0. So basically dot product between 0 and 1 is basically 0. So now let's represent our wave function as alpha times ket 0 plus beta time ket 1, right? So if you project it on the ket x side, so what you will be getting? So you do the dot product between 0 and ket psi, you will be getting, so 0 times 1 is 0, 0 times 0 is 1, so you will be getting alpha. Similarly, if you do the dot product between your 1 and wave function psi, you'll be getting beta. So these alpha and beta are called the probability amplitudes. Probability amplitudes. Amplitudes, or sometimes these are called coefficients. Coefficients. Now, what quantum mechanics says? So whatever measurement you get, right, some psi. So basically, some psi if you get, so some psi of x, if you get a psi is a function of space or time, whatever it is, you need to take the square, which will give the probability of getting that wave function at that particular position or time, right? So whatever alpha or beta you get, if you take the square of this, so basically square of 0 times psi, if you take the square of this, that will give you alpha square. That is the probability, not probability amplitude. I hope it makes clear, right? Okay, there are lots of questions. Okay, so in this, is this connected to image processing? Okay, image is signal. Okay, 2D signal. So there is, instead of so it's the domain is coordinate of both your position vectors, right? It can be your, even if you take a grayscale encoding or even pixels, more dimensions will come. So basically image, this is the thing, is not easy. There are a lot of FQRI and other quantum techniques, specialized quantum techniques for that. This is not straightforward. I'm talking about one dimensional signal, but domain, there is only single variable time or x, and range also there is one. But when I say image, that means there is two coordinates, right? Simply two coordinates. So every x and y, so you get some pixel value or whatever it is. So z is a function of x and y. So this is called the image, and signal is basically, so image typically is a 2D signal. Okay. Okay, there are techniques, specialized quantum techniques for that. Okay, basis states or number of qubits should be larger. Signal is deterministic, but probabilistic amplitude can vary. Won't it be problem? Yeah, there are lots of problem. Okay, quantum is not that easy, but definitely you are squeezing the representation. Squeezing means large dimensional signal you can encode in a lower number of qubit, because if you have capital N number of do I have space? Okay. If you have capital N number of signals, you can encode them with log ceiling function log in number of qubits. So you are squeezing the space. So that means suppose you have 1024 signal values, you can store in using only 10 qubits by using this formula log 2 base n, right? So that means there is a possibility use, but when you are squeezing the space, the algorithm complexity is much higher than the classical part. Okay, so because we are expressing a deterministic signal or probabilistic quantum signal value of Si, when can we use the Bra notation? Okay, I'll take a separate class on that, maybe how it is different from QFT. QFT is an algorithm. Okay, I'm just only telling the basics. What is A, B, C, D? I'm not going to the words or sentences. These are ABCD of signal processing. QFT is an algorithm which basically, if you have some signal X, and if you say it is a quantum signal ket X, what I want to do on X. So if I do a DFT on X, I should get X of T, I should get X of F, frequency spectrum of the signal, right? Similarly, if you do QFT on X, you will get something, some spectrum of X, some say ket Y, right? Something you will be getting. and I'm not covering that. So QFT is an algorithm. It's a matrix manipulation on the vector. But what I'm doing, just definition of KTX and definition of K1. Okay, any connection with quantum cryptography? Definitely there is connection, but this is beyond. Tomorrow maybe we can take all these questions. So, okay, so 3:15. Do I have any further contents? Let's see. Okay, there are many QoS parameters. Okay, there are many things like bit error rate, signal to noise ratio. Okay, so there are things which I already have given you a note. Please have a look. Those who already are teaching this subject, I don't request you to. There is something called Nyquist theorem. Okay, there is something called channel capacity. All these important thing I have defined and shared the material with Professor PD sir. Just please have a look. Probably sufficiently details is given. If you have time, please look at it. And when I say SNR, signal to noise ratio, so tomorrow I'll be covering quantum communication, and let me define another term, SQNR. Okay, so this is the term we have introduced to the literature, that is called signal to quantum noise ratio. Signal to quantum noise ratio. Quantum noise ratio. So let me define this part, because this is not even in the syllabus, or this is not even in the book as well. So suppose you transmit some data from here, you receive from here. This is your X. Power of X is, say, sigma square X is the power of your signal. And in the receiver, you get receive Y. And suppose power of this signal is sigma square Y, right? And SNR, definition of SNR is the received power by the signal power. Okay, if there is the channel and all, there is other things you have to will come into the picture, like effect of channel and other things. I'm not going to that part. The simple definition is sigma square Y, output power of the signal, divided by the input power of the signal. Now, suppose Y is passing through a quantum processing unit, quantum processor, a quantum hardware, right? Now, within whatever algorithm you perform on Y, maybe a quantum Fourier transform or whatever it is, like to get the frequency of Y or velocity, I mean, any time or the Doppler information of Y, whatever it is, right? So you apply some quantum algorithm on it, Q of Y. So basically you will be getting QY, right? So that is, say, some Z, some K Z it may be. After measurement, it can be some classical information, some C, ZC, right? But within the QPU, you are introducing another set of noise, right? Coming from the hardware and all, quantum hardware and all, maybe readout error, maybe coupling error, maybe some gate level error. So there are lots of coherence error, lots of quantum errors. I'll cover tomorrow maybe, and those errors will be an accumulation, right? So those errors will be coming to picture. Then you have something that is called SQNR, that is signal to quantum noise ratio. Now here your signal power is what? So your signal is here, output power is sigma square Y, right? This is the input, right? Now input to the quantum processor. So output by input power. So here input power is sigma square Y, but output power is sigma square Z, right? So now this sigma square Z has something to do, because this particular noise power. So now we know something from the statistical mechanics. So that is basically, if Z is a random variable, which is basically random variable X plus random variable Y, right? So then basically the case is basically, if the random variable sigma X, the associated variance is sigma square X, associated variable is sigma square Y, then the sigma square Z is basically sigma square X plus sigma square Y. I mean, there are complications and all derivations. I'm just leaving it. Just simply the sum of the individual variance, right? So then basically, if you go back to the previous equation, if you replace these things, so this is basically sigma square X plus sigma square Y by sigma square Y. So basically sigma square X plus by sigma square Y plus 1, right? So you can derive more equations like the signal to total noise ratio, STNR and all. So where is SNR plus SQNR is the total noise. So these kind of systems may come into picture in future. For example, in 6G or onwards, beyond 6G and beyond communication onwards, you have a system where you have a classical communication system plus a quantum communication system. where your signal passes through X becomes Y and Y becomes Z, and from the Z you are interested to find some information about X, right? So then basically these kind of things may come into picture. Okay. Okay, so let's take some questions. Since coherence is achieved for very small duration, microsecond, millisecond, how quantum communication takes place in burst? Theoretical question, sir. So I don't know the answer. Maybe you can do research on it and let us know. Okay, yes, material will be shared in Canvas. Okay, sir already told. Okay, so how are we going to use these signals in communication, as the message is encoded in probability amplitude, and when the measure the signal, it will collapse? Yes, this is maybe probably I should. This is beyond the syllabus, first of all, and probably you can look some of the things from the book I referred on quantum information by Mark M. Wild. So the book Wild, you can look at some information will be getting about that. Can more than one operator be represented in quantum signal? Yes. Does probability amplitude differs from each operator? Should be, theoretically should be. Please write the book name, sir. There is no book as such. If I get some opportunity or somebody else get some opportunity should write a book. There are lots of paper. You may look at it in Google Scholar or some other. Okay. Probably this is the end of the section digital communication, and I'm taking some 5 minutes break. You can put all your questions or anything. I'll go directly to the information part. So in the notes, I have given you some of the detection algorithm, like the matched filter, and also the least square estimate for single input, single output, as well as the MIMO communication system formulation of the least square thing. Yeah. All waves can be treated as quantum mechanics. Yeah, the quantum part. Okay, let me go. Who wants to understand the quantum mechanics part, all this probability amplitude? At least they should consult the book Quantum Mechanics by Griffith. This particular book is very good one, so you can directly get from internet. You can order it, or maybe available to your college library. So this is there are lots of books. So even both in digital communication, there are hundreds of books. Like at least the Proakis book is excellent one, and Quantum Mechanics by Griffith or Tambakis. Another book is called written by Tambakis. So that is another good physics books. Also, those who are more and more interested, they can also read the book by Sakurai. So there are lots of books, but the orientation, how it is written, whether using calculus or algebra, that may differ. The language of the big book might be different. There is a newer book on quantum mechanics by Palash Pal. Yeah. So as part of the National Quantum Mission, there are for individual QTs, there are books writing going on. Hopefully, we'll be getting the book soon. So I am also a co-author of two books. And also I am writing one book. The draft is almost ready. It's under review. I hope this should come in 1 or 2 months. I'll be sharing with you all. So yeah, there are excellent materials on the web. Please look at it. Yeah. So whatever materials I do have, I'll share as per with the syllabus and my session with Professor Pilli sir. Yeah. So I'll start the information session, the classical information, Shannon information in 5 minutes. Please take a break. Yeah. Okay, so let's start the information theory part. Um, so first of all, information is physical. Okay, so it's not like that everything is going on the air. So there is a physical hardware responsible for the information. Information can be generated from the classical processor, from your mobile, from some source, okay? And it has to pass through some medium, and it should be reconstructed from some another physical hardware or some physical information retrieval system, okay? So typically in the communication, we have seen that there is a sender, there is a channel, and there is a receiver. So in quantum communication, we'll see the names. Who is the sender? The name is Alice, and the Alice try to send a message, bit stream, some bits, some symbols, basically symbols x1, x2 to xn. Okay, and the probability. So that chooses Alice the message x equals to. So all these particular x1, x2, xn we basically represent through some variable capital X. Okay, and the probability that Alice or the sender choose some message out of X. So there is a dictionary of message, and a particular message that the sender choose, that is the probability of that particular X equals to Xi, and that we call as Pi is known. That means the sender at least know what information it is communicating. Okay, just a question. Can you hear me? Like, am I audible? Can you just, anyone, can you just put a message maybe? Oh, thanks. Yeah. And at the receiver, we already have seen that we are receiving some bit string, some discrete messages or some bit string y1 to yn, and call them as a random variable y because there are uncertainty in between. And when X is transmitted from place A to place B, X is transmitted and Y is received. And in between something, if somebody is trying to steal the message, so two things are happening. One is somebody is introducing the noise. It may be some thermal noise, or it can be some environmental impact on the signal. And there is a distortion by the channel. So suppose there are basically mountain, there are plants, trees, there are so buildings. So whenever signal is passing, it is attenuated by every one of them, right? Attenuated as well as path loss. So there are many phenomena like signal, how it is deferred. In addition, there may be someone, okay, who can try to steal your message X in between. When you are sending from A to B, but somebody C can try to steal your message in between, right? And that is called the eavesdropping. That particular phenomenon is called the eavesdropping by somebody. The name is Eve. Okay. And this particular channel model will be again using in the quantum channel as well. Okay, so very similar thing, but in that particular case, we'll be transmitting KTX. Okay, we'll be receiving KTY, and there is some channel, quantum channel. Here it is classical channel, some H. There will be some channel U. What is that, and details I'll come later tomorrow. Okay. So so suppose I get something X, and I termed the particular thing as information. What is information? Okay. So there is a lots of discussions and literature about what information is. Like, for example, when I was an undergrad student, for me, information was anything. Like any data was information. Any data is information. When I was a master student and PhD student, I saw, okay, information is related to probability, it is related to uncertainty, it is related to probability and uncertainty. So more uncertainty related to some event, that there is more information, that I understood. Now, as part of industry, as part of quantum, I understand information as so that is the quantum information. And there is something more than the probability, more than probability. Okay, why I say more, I'll define this from tomorrow. So for now, let's stick to this part. probability or uncertainty. Okay. So suppose the X is a bit string or the symbols, and getting this particular X is associated with some probability P of X. What I say, suppose you transmitted some signals, okay, and you receive it, and the probability of getting the message X at the receiver is probability of X. Okay. So first of all, to measure this particular quantity, we have to define something, a particular definition. We have to define information. So Claude Shannon defined this information in a very intelligent way, and he called information I that is related with the message X as negative logarithm of probability of X. This is extremely important. Why? So because if it is log 2 base P of X, right? And this is your information probability like P of X. So whatever you give here, right? So this particular information you will be getting in bit string, bits, right? Say, so basically base 2 logarithm is conventionally used, resulting in information measured in bits. This definition captures the inverse relationship between the probability of an event and information it conveys. Rare events, from this definition of this minus, it is also important. So logarithm you can see, because the answer, if you take log 2 bases of something, that means the answer you'll be getting in bits. And the minus is important, means if there is a rare event which has the higher information. Rare events means rare means highly uncertain. Highly uncertain event has more information. Right. So now if you have some random variable X and there is an associated probability P of X, it can be, if X is discrete variable, discrete random variable. So P of X can be the probability mass function, PMF, right? Probability mass function related to that, or it can be some simple probability of X if X is some event. So P of X can be some simple probability, right? And if X is some vector of such all random variables, then P of X can be a probability mass functions related to that. Now, if there is something uncertain, and we have defined information out of it, that how much uncertain it is, I of X, that is basically minus log 2 base P of X, right? So all this is fine. Then the question is, if there is something uncertain and there is, so if X takes some value, say for example, it can be head and tail, it can be your X can be your dice 1, 2, 3, 4, 5, 6. It can be some dice, or it can be your temperature of a day. It can vary. The temperature can vary, like temperature of a day can be continuous variable as well. Temperature of a day, temperature value, or it can be anything, right? Like the stock market price of something. So then this is highly random, like some random quantity. But okay, if there is something, what is so important? Like what can we find out out of this thing? So in statistics, there is something, if there is an uncertainty related with some random variable X or some random event X, then statistics, we can get a lot of information of an uncertain event. And the minimum information that we can get is the expectation. That what is the average information? What is the average uncertainty? Average information. On an average, what we are getting. Variance and other things will come later. But what is the expectation of something? What is the expectation, or what is the expected information? Something is varying. Okay, fine. Like, what is the expected information out of it? So then, in statistics, so basically, if there is a random variable x, we calculate expectation of x, right? Mean of x. Say for example, if in a class there are 100 students, and most of the students has a height between 5 feet to 6 feet, right? And they may be, many of them might be 5 feet 2 inch to 5 feet 3 inch. Some of them can be from 5 feet 4 inch to say 5 feet 8 inch, and this between 5 feet 8 inch to 6 feet, right? But on an average, what is the height of the like average student of the class, right? So those kind of average information we try to get from the probability. Similarly, if you have some ix, that is the uncertainty in terms of the bit stream, right? That is there. Then what is the average expectation of the information, I of x, right? Expectation of I of x. So that is, so when x is some random variable and associated probability mass function is p of x, then we define expectation as x into p of x. So any particular x is xi, right? Out of, if x is a random variable and it has value x1, x2 to xn, then a particular x is xi and the probability is pxi, then the average information is sum of xi and pxi, right? That is the expectation definition. Similarly, if there is an information I of x and expectation of I of x, that is written as h of x, and h of x definition we can write as summation of I equals to 1 to n p of xi log 2 base p of xi, and the unit is bits. Average number of bits that is transmitted from a transmitter to the receiver and perfectly received or not, or whatever it is the case. Okay. So this is particularly a phenomena that is called entropy. So in information theory, you should never remember the definition of entropy. It's just because information is uncertain, it's a random variable. So if it is uncertain, what is the average information? Entropy is a term that measures the average information. Okay, so let me give you two questions and whoever, like, you can put the answer to me. Okay, the question number one is, suppose you are tossing a die, and the possibility, like event possibility is 1 2 3 4 5 6 7 8, right? And suppose this is a unbiased die. First question is, find what is the I of x in bits. Question number one. I'll see who is the first person to answer this. Please put your answer in the chat box. Please do not use any chat GPT or anything. Just try to solve it by definition. Second question is, suppose event has two possibility, head and tail, and also unbiased. Unbiased means probability of both head and tail. Probability of both head and tail, both are 0.5. Okay. So find out hx. This kind of question I'll be asking. Okay. H of x. Find out h of x. Okay. Question number 3. Suppose probability of head equals to 0.9. Probability of tail equals to 0.1. Find out h of x. Okay. So I'll request Pilli sir so to give them reward some way. I don't know how to give them reward. Normally in classes I give chocolates, but I don't have right now to offer. Yes. So the first question, who gave the Nasiruddin gave the first answer. Then Dr. Rajan gave -3 answers. Sir, it will be +3 bits. G Avinash gave the correct answer. Yes. Nalini gave the correct answer. Bipin, yes, yes. This is first answer is 3 bits. So now you know that when you toss a die in your home, you are basically utilizing 3 bits of information. Okay, in the language of digital communication and information science. What is the answer for h of x in the second question number 2? Yes, Rajan Kumar, Dr. Rajan Kumar. Yes, you are correct. Yes. Yes, so I of x is half, but you need to calculate h of x in question number 2. Right. So you see how nice the definition is. Answer is 1 bit. Because the probability is half, and from definition you are getting log 2 base half, right, minus, and that is equals to 1. So remembering the probability is much more difficult than this bit information, right? So this is how beautiful is the Shannon information definition is. And on an average, if you do a binary kind of probability variable like random variable, then effectively on an average, if they are unbiased, you get 1 bit of information. If you have 6 uncertain possibilities, you get on an average 3 bits of information. But if they are biased, like more head is chance, less probable is the tail, then what is the answer for question number 3? Let's see. Somebody gave the answer Q3 as 0.1. No, sir. Please try it again. Just use that definition. Just I gave the definition earlier. So here is the definition. This particular definition. Anyone for the last question, third question? Classical information theory is not that difficult. I'll just define another 2-3 terms and I'll end the session. Quantum information, there are a lot of new things I'll cover next day. Okay, try this question, check it. It should not be 1 bit because earlier there was high uncertainty between head and tail. That's why 1 bit of information. Now you almost know that there is a high chance of head and less chance of tail. Hence, probability of the entropy of x or the average information in this event will be less than 1. Okay, just let me know the exact answer. Not close to 0. Okay, try it. Answer will be yes, close to 0.5. Answer will be 0.469 bits. Okay. Yes, correct. So let's move to the second part, is the conditional probability. What do I have? Conditional probability. And before that, maybe there is a joint probability as well. So if you have 2 random variable x and y, okay, and you have a joint probability, so that is the probability of x comma y. So there is a joint probability. Then the joint entropy is defined as h of xy as double summation x and y, probability of x comma y, joint probability, and log 2 base e x y, right? So this is the PMF, probability mass function, right? And this is the associated information I of x. This is I of x comma y, right? And this is the PM, probability mass function, and this is the expectation. But what it tells is that the joint entropy h of x, y of 2 discrete random variable x and y with joint probability mass function p x comma y measures the average uncertainty of the pair x and y, right? So At the receiver, whatever you have received y is your received signal. If it has some relation, okay, with x as a joint probability relation, then there is a joint uncertainty, like joint average information, and that is defined by this. Similarly, suppose Alice possesses, or the transmitter possesses some message defined by random variable x, and receive signal is represented by some random variable y, which share correlation. This is important. Correlation. And the correlation is what? If they are not statistically independent, means if they are x and y are not statistically independent, means Bob possesses some side information about x. That means if two persons A and B communicate every day, if they are two close friends, that means when A is try to speak some message, and B have some information what A is likely to tell, because every day some prior knowledge B already has, right? So let x and y have some joint probability distribution Px and y. Then the conditional entropy, which is the expected conditional information, that is given by h of x given y, is probability of x comma y and log of Px comma y. So naturally, you know, if B already has some knowledge about X, that means B is not 100% unknown what A will be saying. That means there is not 100% information. That is less information in the conditional entropy. Okay. Similarly, there is called a mutual information. And the mutual information is the difference between marginal distribution H of X and the conditional distribution H of X comma Y. And the I of x comma y is defined as h of x, where highly uncertainty of x is there, h of x minus the side information h of x given y. It quantifies the dependence or correlation of the random variable x and y. It tells how much knowing one random variable reduces the uncertainty about the other random variable. So if you know some information about x already, then what is the uncertainty is there when you receive the signal y. So this is the mutual information definition. So I'll give another maybe last question. So suppose probability of your two coins, suppose head and head is 2-5, probability of head and tail, head comma tail equals to 0.25. That means if you toss two coins, so the first possibility can be, it can be anything between head and tail. And if you toss twice, the events are given as this: probability of head is 0.25, probability of head tail is also 0.25, and probability of tail head, all are 0.25. Okay, tail head is also 0.25, probability of tail is also 0.25. Okay. So means it's a biased tossing. Then now you compute the information, joint information x and y. This is question number 1. I'll give another question maybe. So let me know what is the answer, somebody. Suppose h of y is approximately say 0.971 bits entropy of y. Okay, and h of y given x conditional is say approximately 0.847, right? So find the mutual information. Find the mutual information I, x comma y. So just these two questions. Yeah, the first answer is 2 bits. Second one, Anyone, the second question? Second question, somebody put 1/8, nearly correct. Correct, actually. Anybody else? Any other answer in fraction? Yes, 0.124, correct. So this will be 0.124. Okay, because I have another 5 minutes, maybe let me talk a bit more on the quantum information side. Although I'll be talking tomorrow on it, quantum information side. Now you see earlier, already you have, suppose you have a source, right? And that particular source may be an artificial atom. Artificial atom. So you are creating a superconducting qubit technology. Question X and Y were reversed in the conditional probability, correct? Yeah, so yeah, that is the case. I mean, I just gave one random example. Yeah. Yes, so most of the answers are correct, what is given above. Yeah. So suppose there is a technology which can create an artificial atom, and the technology is there is an say for example particular Josephson junction thing, and so a setup. So maybe it can be a photon polarizer and other things, but let's consider an artificial atom things where you have a ground state energy, ground state, and you have an excited state. Right? These are energy level E0 and E1 of an atom. Okay. So are you writing with a pen or mouse? So yeah, I just I bought a XP pen, something digital slate and pen, but I am writing on top of the presentation itself. Maybe next day I'll totally use some writing pad, writing notebook. So I'll use more colors. Yeah. So sorry if it is not good. So ground state and excited state.
Sir, sorry for disturbing, sir, but I feel your handwriting is quite good and visually it's looking good. So no issues. I guess it's a compliment.
Oh, thank you so much. So
So
yeah,
they actually they all of them are teachers, so they want to understand how you are doing this. So
yes, yes. I thought just to take these classes, I just bought one slate and pen, something like that. So
okay.
there are digital boards, right? So NPTEL recording, similar kind of setting, like recording pen and the pad. Yeah.
Thank you, sir.
Thank you so much. Yeah. So suppose as I talked, as I told you that information is physical, right? And always this is extremely important, even in the age of artificial intelligence. And although I am belonging to a software company, a big company, but I appreciate all the electrical EC engineers and all the physicists who invented the transistors, everything, like even the quantum hardware chips and all, because these all this information are actually working on some CPU, GPU, some chips, right? Similarly, for example, the artificial atoms, you are creating some atmosphere such that there you create some ground state and excited state, few excited state, for example, and you are basically creating all your superpositions, interference, and other phenomena by controlling these energy states of an artificial atom, right? And suppose this is your Ket0 state and this is your Ket1 state, and the associated eigenvalues or associated quantities E0 and E1, and the basis associated basis is Ket0 and Ket1 physically, right? But there is no ideal hardware which can every time create some alpha ket0 plus beta ket1. It is almost impossible. If you create some quantum information, which is a linear combination of some alpha times ket0 plus beta times ket0, it is almost impossible in the practical situation. That means if you repeat the experiment 100 times, so first time you get some alpha 1 ket0 plus beta 1 ket1. Second time, if you repeat the experiment, you get some alpha 2 ket0 plus beta 2 ket1. Similarly, if you run the experiment 100 times, you get 100 such alphas and 100 such betas. Right? So what effectively you get an ensemble of such states, psi1, psi2, so up to psi n, which should be theoretically same, but there will be some change in the amplitude, right? Alpha and beta, right? Because alpha square and beta square are the probabilities and the amplitudes are alpha and beta, right? But there is no perfect hardware. There is not a perfect human being who is controlling, who is designing this information physically and create every time the exact probability with precision, infinite number of terms, if there are large number of terms in the probability, right? So there may be slight variation, right? So you may have an ensemble of such states. This is called ensembles, and there is a separate definition of quantum. So this is a quantum state. So all these are quantum states, right? Quantum states. These alpha and beta, these are called the state vector or the basis vector. Better, I'll say basis vector. And these are the probability amplitudes, right? Now what is happening actually when you run the experiment n number of times, so you are effectively creating quantum state, such n number of states, which should be ideally same, but practically they might be different. So this is a quantum state definition, using vectors, right? Using vectors, column vectors. Now I'll define something called density matrix definition. So instead of defining quantum state in this way, information, these are excellent for quantum computing. There is no alternate. But quantum information theorist, they defined something called a rho as summation of probability and the outer product of these vectors for all I. So if all these states are equally likely, suppose there are two states, so psi1 and psi2, for example, right? Now, if you have a perfect hardware, if you have a perfect state or the pure state, perfect state, then you get psi and psi1 and psi1 by two experiment. So you define a matrix rho as a outer product of your psi1 and psi1. So this is a matrix. So this is basically what I'm doing. Suppose psi is basically, earlier it was alpha and beta. So this is the representation. That means alpha times 0 plus beta times 1. So this is a vector notation 2 cross 1 transpose you can write. Okay. So this is equivalent to this. I mean, just by removing the basis vector, just representing the probability amplitudes of the states, right? So that means it is simply alpha and beta. You can write this way. Now, instead of writing these things, if it is a perfect state or the pure state, I'll write this way: outer product of psi and psi. That means alpha beta. So what will be the answer? It is a matrix alpha square, beta square, alpha, beta, beta, alpha, right? Something like that. So this is a different way of representing. So I'll call this as psi1, which is an outer product of psi1, because the probability is equal for both the state, because it is creating the same state again and again, again and again. So I remove the probability associated with this. Means if you write the summation terms and all, half plus half will be again 1. So this is the definition. So pure state definition is rho equals to outer product of the state with the same state. This is the definition of pure state. Means I have a perfect hardware which can create the same state again and again. But if there is a ensemble, then every time there is an associated. So the first state is this one, and there is a probability associated with this P1 times this matrix psi1 outer product with psi1. The next possibility is psi2 outer product with psi2 with the associated probability P2 and so on. So ultimate equation will be Pi sum of psi I outer product with psi I for all I, and this is called impure state density matrix. So density, general density matrix definition, and this is also representing your quantum state. So we'll start from here from tomorrow. Like tomorrow I'll start from here, like density matrix approach and all for quantum information part, and similarly for QKD and other things I'll give an overview how it works. Yeah. So I'm closing the session, and maybe I can take 1 or 2 questions. I have one meeting. I'll just I'll make aware of that. But yeah, I can take a few questions. Just give me 1 second. Yeah, so thank you so much. For quantum information processing, practically we need to choose such materials where tunnel effect is observed, right? Well, there are lots of technology like hand trap, quantum photonics, NV center, or superconducting or topological. So it is not necessary for every technology, but some technology it might be an option. Sir, any textbook for this understanding of quantum communication? Definitely, I just beginning, you just see the initial slides, or you can just restart the lecture in YouTube or somewhere. You can get the references again. Thank you so much. Thank you, quantum HPC communication, which might. Okay, this is an like quantum communication HPC, which may be helpful for us. Both are useful. Okay, you can never neglect an existing technology. HPC has a lot of good advantage, but quantum is a different technology. For example, if I say I have a bulb which is discovered by someone, right? So can't I use the candle? Okay, I should use the candle, but it has a dedicated purpose now. But bulb has a better perspective right now, like tube light or like CFL bulb, right? So these are two different technology. Okay. Coherence, since coherence is achieved for very small duration, how quantum communication takes place? Okay, maybe tomorrow I'll come to this question. I'll take this question, sir. Yeah, thank you very much for this coordination, and any other thing maybe we can take tomorrow. Thank you so much.
Thank you so much, sir. It was a wonderful session, and like participants have already pointed out, handwriting and visually also it was quite appealing. And thank you. Do you want to add anything more, sir?
No, thank you. So tomorrow again we'll see. Yeah, I have one meeting. I'm so sorry.
Okay, okay, sir. Fine. So we'll continue tomorrow then. Thank you, sir. Thank you.
Thank you, sir.
Thank you, Ashish, sir. Adi.
Thank
Yes.
you, sir.